Live from the University of Texas at Austin, the Liberal Arts Development Studios present Essentials of AI for Life and Society. And now, here are your professors, Joydeep Biswas, Don Fazell, and Peter Stone.
Hello, and welcome to the second lecture in our class, Essentials of AI for Life and Society. I'm Don Fazell, the chair of the CS department, and I'm happy to introduce us to the next section of topics in this course. After the introduction that we had last time, we're going to talk about some of the classic problem areas that have been tackled by what we call artificial intelligence these days. And I'm happy that we have with us today another of our instructors, Joydeep Biswas, a member of our department also, who's an expert in robotics, planning and search, and is going to talk to you about planning and search. So with that, I'll turn this over to Joydeep.
Thanks, Don. So as Don said, my name is Joydeep Biswas, and I'll be talking about planning, all right? So to just dive into it, I want to ask a question. What's common between the following?
Come on, Charlie.
All right, okay. Here we go. All right, ready? Yeah. Turn. Okay. Turn. Turn. I don't think we can turn anymore.
And the next video. Well, the gist of it is the commonality between the last two clips were essentially planning, right? And hopefully by the end of today, we'll actually get a better understanding of what I mean by that, right? So what is planning? So to understand what the planning problem is, here's what we need. So given an initial state of the world, a set of available actions, their requirements, and their effects, a goal state, and optionally costs associated with each action, the planning problem is to compute a valid sequence of actions, the plan, that starts from the initial state and terminates at the goal state with the fewest actions or the minimum cost, okay? All right, so this is something which is probably familiar to you if you've read the weekly reading. So let's take a quick poll on this topic. So which of the following are required to define a planning problem? Select any that's a correct option. The initial state, the programming language of the planner, a set of available actions, or the computer serial number. All right, I think that should have been enough time for you to think about this question and respond to it. The answer is it's either the initial state or the set of available actions. Both of those are correct responses, okay? All right, so to get some understanding as to how we solve this planning problem, let's look at a simple problem, right? So this is what's called a toy planning domain. It's called blocks world. And in this scenario, what we have essentially are three blocks, A, B, and C, right? There's a table, and there's a robot gripper, right? And the actions that the robot can take is that it can pick up a block if the gripper is empty. It can put down a block when holding one. It can either put it down on another block or on the table if the block is if the other block that you're trying to put it down on top of is free. Okay. So the assumptions here are that there are no errors in picking or placing the blocks. So this is not a fine-grained manipulation problem. This is more about a conceptual problem of how do you stack these blocks, right? And the table has ample space for all the blocks, right? And finally, the assumption in this particular scenario is that the horizontal positions are irrelevant. So in my image over here, you see that the A is to the left or to the B, but we shouldn't pay too much attention to the exact ordering of them, right? So the thing that we care about is what are the stacks of these blocks that we have. So for example, on the left, they're all on the table. On the right, they're in a stack A, B, and C, okay? So how do we actually solve this problem, right? So let's see how we can apply the planning problem, apply to blocks world. So the initial state now is the initial state of these blocks. The actions that we have are pick a block and to place the block on some location. And the goal state is a final state of blocks, okay? The valid sequence that we have is going to be a sequence of pick and place actions that the robot takes, okay? So to solve this problem, one way you can solve this is using what's called search, right? So planning via search. So essentially what you do is that you start from the initial state, you enumerate all possible actions available and the resulting states, and you check if the goal is reached. If the goal is not reached, for every possible outcome, you repeat step one, and you keep doing this over and over again, right? So to walk through this algorithm, let's look at an example, right? So let's say we have a simplified blocks world with just two blocks with A and B. So A is on top of B, right? And our goal state needs to have B on top of A, right? So somehow we got to swap these, right? So how do we do this with search? So you start from the start, right? The only action that you can take right now is pick up block A, so you do that, right? And now you have two options. You can either put the block A back on B, or you can put the block A on the table, right? So these are the two outcomes. And for each of these outcomes, you have other options available to you, and you keep doing this. And eventually what you find is that after applying a sequence of actions, you eventually find that you've reached the goal, right? So once you find that you've reached the goal, you backtrack up this tree, and the plan is essentially the sequence of actions which took you down to the tree to the goal, okay? All right, so this sounds great, but many real-world problems quickly become intractable to solve using this search-based planning problem, right? And the reason for that is that there are too many actions, and there are too many branching options, and it's unable to enumerate till the goal is reached, right? So what are some key approaches or key ideas that we can use to actually overcome this problem? So first of all, if you go back to this scenario that I showed you, you find that there are actually duplicated states. So if you pick up the block A, right, and put it down again, you reach a state which we've seen in the past. So essentially, all the subtrees of this state are going to be the same as what you've seen in the parent. So you actually don't need to go down the subtree anymore, right? And the same is for this the state that you see in the red over here. These two states are equivalent, right? So one key technique is pruning, so removing subparts of the subtrees which are equivalent to things that you've seen before to reduce your search space, okay? A second key thing to note over here is that there are some actions which don't seem to make progress. So if you pick up a block and you put it down again, and if you pick it up again, you're going in this loop, right? You're not making progress towards your goal, right? So how do you make progress towards your goal, right? So one idea of how do you make progress towards your goal is to use what's called heuristics. Okay, so in the planning community, heuristics means something very specific, and a planning heuristic is an optimistic estimate of how close a state is to the goal, right? And this optimism is actually somewhat important if you care about optimality, if you care about like shortest sequence plans, right? And one way to use heuristics with planning, there are others of course, are to prioritize taking actions that have better heuristic scores. So let's say you have multiple options available to you. You compute the heuristics of all of those options, and you pick that action which has the best heuristic value. So what is an example heuristic in this domain, right? So the optimism. So let's say you have an initial state with these blocks on the table. You have the goal state with A on B on C, right? So the way you think of the goal condition is that what are the goal conditions, right? So you need to have A on B, right? You need to have B on C, and you need to have C on the table, right? And initially you have A on table, B on table, and C on table, right? So here's an optimistic estimate, right? You can assume that these goal conditions can be independently achieved somehow, right? Which is clearly not true, but we can assume that that's the case, right? And then the heuristic value then becomes how many of these goal conditions have you met, right? So let's see how that would actually work. So let's say you are picking up a block, you've picked up block B, and you're trying to ask what should you do next, right? And your goal condition is to have this, right? So let's say you have multiple options where you can put the block B back down on the table, or you can stack it on C, or you could stack it on A, right? So you have these three outcomes, and in these three outcomes, the number of goals satisfy is the same except for the one in the middle. In the middle, it turns out that this condition B on C suddenly gets satisfied, right? Previously, it was not satisfied. So since this state is actually making progress towards your goal, it's actually satisfying part of the goal specifications, the heuristic would value that more highly and would prefer that to the others, right? And that is one way in which you can use heuristics for planning via search. I'd warn, however, that there are actually problems with using pure heuristics and only being guided by heuristics. If you want to think about what problems you might encounter, I've actually given a scenario over here. So let's say the initial state is C on A on the table, and B on the table. And you pick up the block B. If you apply the heuristic exactly as I've told you, the planner will end up doing something which is actually counterproductive, right? I encourage you to, after class, think about what it would do and why it's counterproductive and actually how to overcome this. So this is actually a problem which has been studied extensively back in the 80s, and modern day planners don't actually have this problem, but if you are guided only by a heuristic, you might actually face this problem, okay? All right, so we've been solving planning problems in this toy domain using blocks. And we know how to rearrange blocks on table, which is great for maybe solving mobile phone games and all. But we are asking questions about the bigger, meatier questions, like what is intelligence, right? And we want to ask, how does planning relate to intelligence, right? Well, one answer to that, which is something people thought about for a long period of time, is maybe doing things like play chess, right? Because once upon a time, there was believed that a mark of intelligence was in how well you could play this really complex game like chess, right? It turns out that you can use planning to play chess, right? And the way you do this is you take our problem definition of planning, right? And you actually make that specific to chess, right? So your initial state is now the current state of the board, right? The available actions are the valid chess moves, right? And the goal state are the checkmate conditions, right? And the valid sequence of actions that you will take will be the sequence which obey the rules of chess, right? And the plan is going to be the sequence of chess moves that take you to the checkmate conditions, right? Now, you can't actually apply planning via search exactly as we've seen before, right? And the planning via search, what we had said is you start from the initial and you enumerate all possible actions, etc. But now you're actually playing against an opponent, right? So to do that, we actually make a slight modification. We do adversarial planning via search, right? And here's how you do adversarial planning via search. So first, similar to in the previous approach, you enumerate all possible actions available to you. But now, after that, you enumerate all possible actions available to the opponent, right? And you keep doing back and forth until the game ends, right? And when the game ends, for each level, whether it's you or your opponent, you pick that action which was most favorable, right? So when you're backing up from the end of the game, for your opponent, you want to pick that action which was most likely to lead them to win. For you, you want to pick the action which most likely leads you to win. And then when you back up all the way to the top, when you've rewound all the way back to now, you just pick the most favorable action, which is the one which results in the most number of games won, right? This is actually not actually feasible. And the problem here is that there are just way too many game outcomes, and exploring them all will take way too long and exhaust computer memory, right? All right, so this is a problem, right? Now is a good time to actually pause and take another Insta poll. OK, so here's a question. What makes search-based adversarial planning hard when playing chess? The options are there's no home crowd cheering for it, there are no goal, the goal condition is undefined, it's infeasible to evaluate all possible outcomes, or that moves are not well defined. All right, so that should have been enough time to think about this question and actually answer this. The correct answer is that it's infeasible to actually evaluate all possible outcomes, right? Okay, so to solve this problem, right, we're going to make some small modification, which is using an idea that we've looked at before. So we're going to use heuristics, which we've seen before, but now we're going to use a slightly different form of heuristics, right? So first of all, instead of repeating 1 and 2, which is this enumeration, until the game ends, we're going to cap how far we look ahead into the future. So we're going to cap how many steps into the future we look ahead, right? And now, instead of if the game does not end in that much time, you use some heuristic value of the game state, right? And in chess, there are some well-understood values that you can ascribe to based on which pieces are there on the board, right? So you ascribe numerical values to the pieces on the board, and also you can ascribe value to which squares they are on the board, right? And using this, you can compute a heuristic value of these game states, right? And for each level, when you're actually backing up from the bottom of this tree, you end up with this tree like here. You pick the best value for this player using these heuristics, right? And at the end, you pick the most favorable action. Okay. So this seems like a simple enough algorithm, but it's actually really effective. In fact, in 1997, Deep Blue, using an algorithm which is similar to this and some clever strategies, but also with some secret sauce, which are essentially special computer chips designed to speed up enumeration and evaluation, specifically of chess moves, they were used to actually beat Garry Kasparov in chess, right, who was a world champion. And on the right, I show you the computer as well as the paper which outlines Deep Blue, the algorithm, as well as the hardware, right? And fast forward to today, actually, within the last 2 weeks, this paper, which I just showed you, Deep Blue, actually won the AIJ Classic Paper Award at HCAI, which is one of the top AI conferences. So going back to 1997, right, we said that one mark of intelligence is being able to play chess, and there we had computers beating the world champions in chess. So was AI solved? Right? This really raised the question. It's like, we thought that chess was the epitome of intelligence. And clearly, computers were able to beat the humans at chess. So was AI solved? Well, the answer is not quite. And to understand why, I bring back the slide which Peter Stone had shown, which is defining artificial intelligence. And as he had mentioned, it's more than one thing. It's not just deep learning. It's a bunch of other things, including planning, which I've put in bold because we're looking at planning. But there's another tongue-in-cheek definition, which is getting computers to do the things that they can't do once it works. It's engineering, which is kind of like a tongue-in-cheek thing to say. But on the other hand, this is actually true. We set ourselves to beat a milestone. We meet the milestone, and suddenly we say, well, that wasn't quite it. Maybe that's not what intelligence is. And this has actually happened several times in the history of AI, right? But there's actually deeper criticism that you can make of this approach of actually coming up with a chess-playing AI agent. First of all, there are games like Go where even steps 1 and 2 are intractable even for a few number of steps. It's just way too complicated, right? And secondly, one thing which was crucial for Deep Blue to win is that there were specialized chips only for playing chess and nothing else, right? And we don't want to create special purpose computer chips for every single specific problem, right? We want something a little bit more general, okay? Now, to take a page out of Peter's book where he talks about like how it's more than just one thing, outside of the planning world, lots of things were happening around 2012. In the computer vision community, these things called deep neural networks started gaining steam, and that's a story for another lecture on computer vision, which you'll get to see in a bit, right? But it led to, in 2016, AlphaGo defeating Lee Sedol at Go, right? And the key to this was something rather interesting, and I want to play a video to go over that.
There's the policy network, which was trained on high-level games to imitate those players. And then we have a second component, we call this the value net. And it can evaluate the board position and say what is the probability of winning in this particular position. And then third component is the tree search, where it would look through different variations of the game and try to figure out what will happen in the future. So if we now take a position like this, First, the policy network would scan the position and come up with what would be the interesting spots to play. And it builds up a tree of variations, and it then employs this value net that tells it how promising is the outcome of this particular variation. So AlphaGo tries to maximize its probability of winning, but it doesn't care at all about the margin by which it wins.
All right, so we saw a clip of the key insights of how AlphaGo actually works. This is taken from the AlphaGo the movie, which I highly encourage everyone to watch. But let's come back to this algorithm of adversarial search, right? The key changes that happened, and I'm of course simplifying a lot of this algorithm, is that instead of actually enumerating all possible actions, you enumerate promising actions which are generated from this policy network, right? And then instead of using like hand-coded heuristics to come up with values, you use a learned value, which is from a value network at the leaves, right? So using this, it turns out that this key idea of tree search plus guided by deep learning is actually really powerful, right? But coming back to this problem of autonomous cars and Ross's couch problem, right? How do we actually deal with that, right? So at least now you agree that planning can be used to apply to solve problems like the blocks world, which are symbolic problems, and we can use it for solving things like or playing well in games like chess and Go. But what about something more complicated, something that moves in the real world in continuous spaces, right? So here's how we might approach it, right? So here's a planning problem applied to autonomous driving, right? So you have your initial state, which is a current car pose and velocity. When I say pose, I mean the location as well as the orientation, right? And the set of available actions to you include the safe driving actions, which are the steering and throttle. Interestingly, the only commands that you have, the only controls that you have over your car are the steering and the throttle. You can have like communication actions like the turn indicators, but to move the car, you only have the steering and the throttle and brake, of course, yeah. Now, the goal state is your driving destination. So if you're trying to parallel park, it's like the position that you want the car to be at, right? And the valid sequence of actions is a sequence of driving actions which take you from the start to the destination location, okay? And we'd said that using search, the way to do this is enumerate all possible actions available and the resulting states and keep doing this, right? You can't do this in this planning domain. And the reason for that is rather simple. Your states are continuous, your actions are continuous, so there are actually infinite actions available. You can't enumerate all of them, okay? So how can we actually plan with continuous actions? So how can we plan for a continuous sequence of actions to take, for example, this car on the left to the goal on the right, while avoiding obstacles like this wall over here, right? So this is what's called the motion planning problem, also known as the piano movers problem, also known as let's help Ross plan for how to move his couch up the stairs, right? All right, so this is how this one algorithm solves this problem, right? So this algorithm is called rapidly exploring random trees, and it's actually rather simple, right, rather easy to understand. So you randomly sample a state, right? So when you're posed with a hard problem, what do? You guess, right? So that's what this algorithm does. It just guesses a state. And then it tries to get to this new guess from the closest known pose that it knows about in the past. If it's able to drive to there without a collision, then it will expand the tree as a possible action. If there is a collision, then it will discard that and draw a new sample. And you keep doing this, and you build this tree over space until you reach the goal, okay? I'm skipping over some details over here, but essentially this is what the algorithm's doing, right? So let's walk through this, right? So let's say you're starting from here and you're trying to get here. You sample a random state, which is shown in gray, right? And the car can't get there exactly because it's too close and it's exactly parallel to where you are. So maybe it can get to some place which is very close, right? And you declare that success, okay? Very good. You draw another random state, okay? And now the closest state to this is the root node that you had over here, right? And you come up with another sequence of actions continuously to get to that, right? You draw another sample, right? And now the closest node is this one over here. And you try to come up with a sequence that will get you from here to there as quickly as possible. And then you do that and realize, oh, wait a second, if I did that, I would actually hit this wall, right? So you discard this option because you can't get there in an obstacle-free manner, right? And you go on, and the algorithm will draw a new sample. It'll connect that. You draw a bunch of more samples. And eventually what happens is that you find that the tree gets you to the goal, the destination, okay? All right, so once you have done this, you can, how do you get the plan back? You backtrack up the tree and see the sequence of actions which actually led you there. And that's the answer. That's the solution. That's your planning solution, okay? So let me show you a video of actually applying this to the real piano movers problem, which is essentially to get a grand piano from one location to another location, given that you have a detailed 3D map of your apartment. So if you come up with a 3D model of your apartment and you have a 3D model of your grand piano, you can use this algorithm to actually come up with a sequence of actions, right? So let's watch this video. Okay, so on the bottom right, this video is actually taken from a particular paper, and actually they're trying to show the efficiency of the algorithms. On the bottom right, you can see that it has drawn multiple samples, but actually has connected the solution via the samples drawn to come up with a valid plan to get the piano from the start to the end. Okay. Okay, so this is great. And I've given you some ideas of how we might address this planning problem. And it's clear that we are making progress. So let's ask the question again. So we're not going to ask whether AI is solved, because we know better now. But can we ask the question, hey, is planning solved? Is that all that needs to be done, right? Well, the answer is maybe not, right? So to understand why not, let's go back to the planning problem. So in the planning problem, we had an initial state. We required an initial state of the world. We required the enumeration of the available actions, their requirements, and their effects. We required the goal state, the costs of these actions, right? And then we needed to compute the valid sequence of actions, okay? But in this, there are actually there's a lot of open gaps, right? So for example, what if the initial state of the world is not fully known to you, right? What if you're trying to pull a box and you don't know what's behind it, right? You don't know what's going to happen next, okay? What if the requirements and effects of actions itself is unknown, right? So what if you're driving at high speed on ice, right? And the effect of doing certain actions might be hard to predict, okay? What if your goal state itself is ill-specified? What if you want a planner to, for example, plan an awesome hiking trip for you, right? What does an awesome, quote-unquote, awesome hiking trip mean, right? Finally, the costs associated with these actions themselves might not be easy to specify. An example of this, a canonical example of this, is whenever there's humans involved, right? The cost of taking actions alongside humans is actually very hard to specify mathematically, right? So an example is social costs of actions, right? One of the canonical problems in robotics is social navigation. So how should robots move around such that not to be nuisances and to move like the way humans would, right? Which is, don't get too close to people, don't cut people off. But these things are very hard to specify mathematically, okay? Okay, so we've seen a lot of planning algorithms, several applications, and challenges. Now, I'm curious to hear your thoughts on the topic. So here's an Insta poll, right? Okay, so select any that you agree with. All right. I believe that should have been enough time for you to respond to that. So in summary, I want to just recap what I've covered. I briefly described the planning problem, right? We looked at 3 applications of planning, including symbolic planning, adversarial planning, and motion planning, right? We looked at 3 approaches to them, which were somewhat related but had their unique flavors. So search with heuristics, adversarial search with heuristics and with learning, right? And finally, we looked at rapidly exploring random trees, right? And then I finally briefly touched on what are the open research problems in planning, okay? All right, so thank you for attending today's class on planning. Hopefully this gave you an idea of an understanding and appreciation of the planning problem in AI. I'm happy to take questions now.
Okay, well, our initial question was, chess and Go are games of complete information, whereas driving an agent must operate with incomplete information. How does the tree search account for the outcomes of each action being uncertain?
Yeah, that's a great question. So there's several sources of uncertainty, right? So there's uncertainty in the actions that you take, and there's uncertainty in the observations that you that you make as well. So when you get an observation, when your sensor says that the wall is, for example, 1 meter away, it's not exactly 1 meter. It could be 1.01 or 0.98, etc. So the question is, how do you take this into account? So actually, very conveniently, in the next lecture, Professor Roberto Martin is going to talk about reasoning under uncertainty. But to answer you briefly, what you do is that you maintain a belief or a distribution of the possible outcomes which are consistent, which are probabilistically consistent with both your with your probabilistic models of how to act in the world and probabilistic models of observation. And then you look at the belief, right, and say, based on the belief, you can do a couple of things. You can say, based on my belief, what's the most likely result, which makes sense. Or you could say, if you want to be cautious, which is to say, I have some uncertainty as to whether I should take a left now or a little bit later, you can choose the most conservative action, which takes into account your uncertainty. So these are some ways in which you might want to reason about uncertainty. It depends a lot on specifically what application you're doing, applying this to.
Oh, well, that leads into another question, which is what kind of intelligence requiring problems do not get solved via planning?
Ooh. This is a great question because there is a canonical view of artificial intelligence, which is that you have an intelligent agent. I wondered whether I should put it in my slides, but maybe I should have, because clearly this question came up.
Yeah.
One view of an artificial intelligent agent is that, look, an agent gets some observations from the world, it takes some actions, and the actions go to the world, right? And the world takes that actions, and the world changes, and you get back some observations. So from this perspective, at a very high level point of view, it seems like everything is planning in principle, right? But it turns out that you can't actually solve that. Not all problems can be solved in the manner that we have done with planning, in the sense that you can't actually reason about the sequence of actions and all of the possible outcomes. Like, you need to act a lot faster than that, right? So searching is hard and intractable. In very often, there are problems which you can formulate as a planning problem, like what we call a Markov decision process or a partially observable Markov decision process, but we don't necessarily exactly solve them that way. We can use that framing. Sometimes the formulation of the problem itself is interesting. It's illuminating, even though you don't solve it exactly using planning. Okay. I don't think I fully answered the question of which you can and cannot, but at least hopefully I provided some insights about how to think about this.
So there were several questions that had to do with efficiency of search, and I guess not defining efficiency. So for example, isn't random search inefficient in a way?
Yes, random search is indeed rather inefficient, which is why while I had explained the vanilla algorithm for the rapidly exploring random tree, you might think about a couple of ways in which you can make it more efficient, right? So one example is that the algorithm that I explicitly showed you, it'll take a long time to get to the goal. So sometimes instead of always drawing random positions, sometimes you just probabilistically just say, hey, can I just try to get to the goal now? Are any of my nodes on the tree currently able to get to the goal? This is what we call a goal bias, right? And in general, the general idea is that instead of picking pure random, you want to use some information to draw these random samples. And this is what's called informed sampling in these sampling-based planners. And there is a hot area of research in understanding how can we learn to come up with better samplers. So these need to take into account some notion of what is hard in your environment, right? Which are the narrow gaps in the environment that you need to pay attention to? Okay. Yes, I think there's a question in the live audience, which we're happy to answer.
Piano movers problem, like with the autonomous cars.
So the question is, how does control theory play a role in the motion planning problem? Okay, so just some terminology. So the control theory problem is essentially asking if you have a model of how a system behaves, how can you compute a sequence of controls to actually get it to do something? So there's a historical aspect to this question, which is that the similar kinds of problems have been looked at in different communities. So in the AI community and the computer science community, we call it a planning problem. In the engineering discipline, this has been called a control problem. But we're increasingly coming to understand that these are essentially multiple different ways of looking at the same problem. So you can frame a planning problem in a controls format, right? And you can frame a controls problem in a planning format. So I don't see the two as being fundamentally different. There are historically different tools that people have taken. So in planning, people have taken algorithmic and data structure approaches to like solving these problems, whereas in the controls community, people tend to take much more mathematical tools, like coming up with a calculus of variations to come up with optimal solutions. But they're essentially different ways of looking at the same problem.
Okay. I noticed that many of these problem-solving pathways have a rule book that kind of dictates the actions that can be taken to accomplish the goal. Are these limits to the actions that can be taken set by the programmer? And if so, do you think that AI will ever develop its own rules for accomplishing the task?
I'm not sure I entirely agree with the premise of the question that there needs to exist a rule book. I guess in some sense, like the rules have to be that things that you cannot disobey, maybe. So in chess, you're not allowed to like move a knight's piece, which is illegal, right? So these are rules that you have to obey with. But I don't think there's any hard and fast thing that you have to take certain actions which come from a rule book. I think. In fact, most researchers would say that having a rule book is kind of cheating. It's like we don't want to do rule books.
You mean like they use in chess at the beginning?
Okay, so there's like where does a rule book come from? If you come up with a rule book automatically, if a computer comes up with a rule book and says, okay, I played 1 million games, and of these 1 million games, I found like these small set of initial moves tend to do well. That's an automatically generated rulebook, and we're all for it. But I think in some sense, having a human to tell the computer that these are the things that you should do to win, in some sense, that's a little bit cheating from the AI perspective. So if the rulebook is automated, I think it's great. But I wouldn't. I don't think we need to like hand code many of these rules in these things anymore. Yeah.
Let me echo the TA. We're not going to get to anywhere near all of these questions during this session, so they'll be discussed in the discussion sections.
Definitely.
So if we don't get to yours, that's okay. It can be discussed later. What's the thinking about how quantum computers will impact planning AIs? Got any thoughts about that?
Oh, well, that'll be interesting. I think. In fact, I do think I remember seeing some work where using annealing, you could actually come up with plans very effectively and very quickly. I think the problem then becomes like, how do you reduce a problem that you're trying to solve in a manner that the quantum computers can do? And that is actually a hot area of research itself. Like, how do you reformulate a problem that you're trying to solve and that we have the hardware to be able to do? How is it going to affect it? Hopefully, it'll speed things up. Yeah.
Well, I know that we have Scott Aronson talking later in the semester, so you might consider asking this question when Scott's here.
That's correct. Yes.
Are multiple goal problems tractable?
So when you have multiple goals, the question is, how are you trying to deal with the multiple goals? Are they sequential, or are you trying to hit any combination of them, or are you trying to satisfy any one of them? And there indeed are applications where we do each of them, right? So I would say amongst all of them, the easiest one is where you have a goal set where there are multiple correct answers, and you can get to any one of them. In some sense, that's a little bit easier because it gives you options. It gives a planner options. The harder one is that you have to satisfy multiple goals, and you're not given an order in which to hit them, right? This is actually a big problem, and this often shows up, right? What is the other? Yeah, I guess
that was it.
Yeah, that was it. Okay, right.
Well, here's one that's a little different.
Yep.
What's the most surprising, unexpected outcome you've experienced?
Oh. So it's interesting that when you deploy planners in the real world, they come up with solutions. They designed, in some sense, planners are actually problem solvers. Like you codify the problem in a formal manner, and you have a scenario in a formal manner, and you get a solution out. So sometimes these solutions can surprise you in the sense that, I would not have thought of that solution. So certainly, we've looked at, we deploy planners on robots for doing things like path planning, and we've also deployed planners for things like robot soccer. So Peter has worked a ton on like robot soccer. I've also worked a little bit on robot soccer. And sometimes, like the strategies that they take, like the sequence of actions that they compute can be exciting and surprising, and you wonder, that is unusual. I wouldn't have expected that to happen, but it does, and it works. So that's cool. Yeah. One example of that is that we deploy our robot on campus, and sometimes the robot finds a narrow pathway to avoid like crowds, and it's able to take it, and we're like, okay, that's cool. Yeah.
Here's one we've touched on a little bit. How can human expertise be integrated into planning algorithms? Perhaps for problems where humans have some useful expertise but are not able to solve the problem themselves.
Okay, so that's a great question. I think, how can you have humans assist in planners when they're not able to solve the problem themselves, but they have some insight of this? So this is actually a hot area of research. Several researchers here including Peter Stone and I think Scott Neekum, who used to be here, worked on that as well. He's at UMass now. But their idea is, actually a lot of the common ideas are, even though you don't know how to solve the problem, you can actually provide advice on what are better approaches towards better actions to take, right? So you don't know what the full sequence of correct actions is, but you can say like this partial sequence is better than this other partial sequence. And when humans provide this feedback, a learning agent can use this feedback and actually produce the full sequence, which the human might not have been able to come up with, right? And in some sense, this kind of makes sense, right? When you're watching a soccer game or a football game, I think most of the people watching football or soccer are not necessarily the best at that, but they can provide advice like, oh, I don't know how to do it myself, but I think clearly that was the wrong thing to be doing, right? So, and this is true for like learning agents as well.
How do machine planners take into account the limitations of the environment or the machinery, for example, in the case of robotics?
Okay, so this is a great question about reasoning about your limitations and understanding how to account for them in plans. Okay, so let's see. So you can tell so when I had said like the set of actions available to you, the planner needs to be given the set of actions available to you. Sometimes these formal definitions include the limitations that, for example, you can codify that the robot can drive at X speed, but it can't do that on ice. It can only do that on gravel or concrete. And if you provide that as an input to the planner can take that into account when generating the plans. Sometimes it can always also let the planner say, I don't know how to solve this problem, or at least given the problem that you've given me and the constraints that you've given me, I don't know how to do it. But this also leads to some interesting work where if a robot has limitations, like maybe it doesn't have an arm, the robot can actually ask others, like humans, for assistance. So this is rather interesting. And another facet to this problem, of course, is having the robot themselves discover their own limitations. So they try to take an action in the world, they might not be necessarily as good at doing that, and then they realize that, and the next time they account for the fact that they made this error. And this is what we call competence-aware planning. Okay.
Will there be a time when a machine can do all planning?
So interestingly, although I provided like a cohesive view of many of these planning approaches, under the hood at the lowest levels, there are some techniques which are good for some types of planning, and there are other techniques which are good for other types of planning. Like, so I mentioned approaches which are good for symbolic planning, and I gave a different algorithm which was good for like dealing with the real world. I think having a single algorithm which can deal with any arbitrary plan with any arbitrary constraint is going to be a rather hard problem. It will definitely require, I don't know if we will be able to do it, but if we are, it will necessarily draw on all of these ideas rather than do one. There's no one rule, one single approach that rules them all. It'll have to be like a combination of all of these.
Here's a question about the reading.
Okay.
The author mentioned time as a component of basic ingredients of planning. Well, if and how does it play in planning?
Great. Okay, so time plays an ingredient in several different ways. So one way in which it plays a role is that when you're working in the real world, you care about like good plans, but you also care about satisficing in the sense that you can come up with a better plan. Let's say you come up with a valid plan which solves your problem in like a minute, but then if you give it an hour, it will come up with a plan which is like 10% better, in which case it's probably not worth it. So the question is like, how much more time would it take you to actually improve upon that plan, right? So that's one, this is what we call a meta reasoning problem. How do you account for like how much time do you have to generate better plans, right? So that's one way time plays a role. The second way time plays a role is that the plan itself can be a timed plan. So each action can take some amount of time to execute, and you need to account for that, right? So when you say first do this, then do that, etc., and especially if you're like trying to coordinate with multiple agents, you need to account for like how long each of these actions will take. But one easy way to think about that is that, hey, time is just another dimension. You can only move forward in it, but it's a continuous dimension, and just include that in your planning problem. So I spoke about operating in X, Y, and theta. You can actually operate, you can come up with plans which operate in X, Y, theta, and time, right? And if you do that, then your plans can deal with dynamics.
All right, well, I think we're out of time for questions. Let me just conclude today by letting you know what we're doing next time. And it shouldn't come as a surprise that you need to learn something about probability. You may have heard of Bayesian reasoning, and you're going to learn about Bayes' rules, how probabilities are used in robotics, what are the risks of using wrong priors, and even what is a prior, since I'm sure you've heard of that. We'll have Roberto Martin with us.